Hi, this is going to be the third video in the enthalpy changes section, and this covers the average bond enthalpy and average bond enthalpy calculations. So I'll quickly go through what that means, and then we'll look at an actual example of this as well. So, bond enthalpies, first of all, are the average, and this is it, we take a mean. I'll come to this in a bit more detail in a sec. Average amount of energy required to break a bond. Or, as well as that, it's the amount of energy released when a bond is formed. So we've got two different things there. Amount of energy we need to put in to break a bond, amount of energy that's given off when a bond is formed. And what we can then do is, if we have a reaction and we look at all of the amount of energy that is in the bonds in the reactants, and we take away the amount of energy in the products, then we'll get the average bond enthalpy. So that's what we do. So average bond enthalpy equals energy required to break bonds, or the total energy required to break bonds in the reactants, minus the sum of all the energy in the bonds formed. This is slightly different to the enthalpy changes that we did earlier. Those calculations generally have the sum of, we take the energy in the products and minus the energy in the reactants. So it's slightly the opposite way around to that. And it's just to do with the fact that's the energy completely in both bonds. This is, here we've got the energy breaking the bonds. This is the energy released when the bonds are formed. So just slightly different things when measuring in these. So, example of this. Is shown here. And if you have a look at this calculation, first of all, we've got the average bond enthalpies. So we've got CH, COO, OO, OH, CN, CCC, CC, and HH. And it's the average bond enthalpy, because although CHs are pretty standard, we've got 413 here, we could have a CH like we've got in CH4. Looks like that. We've got the CH bond. This bond, the enthalpy in this bond will be affected by the free CHs around it. So this one, CH bond, will be affected by the two CHs around it, but it's also affected by the OH. So it'll have a slightly different bond enthalpy. And so we take an average and put this here, which is one reason when we do this experimentally, we might get slightly different values. The classic version of this that gives you slightly different odds is if we look at the carbonyl bond, COO, and if we look to that in an aldehyde, so methanol, and compare that to ethanoic acid, if we did this experimentally, there's quite a big difference between these two, because this OH really affects the strength of that bond, whereas in this one, no OH, so no, well, H is slightly affected, but nowhere near as much as that OH does. So you get differences experimentally. We take an average of these to work out what this 805 would be. So, in this calculation, we've got methane, CH4, plus 2 oxygens going to CO2 plus 2 H2O. And below we've got all the different types of bond. So methane is just 4 CH bonds. Oxygen, or O2, is O double bonded to another oxygen, and we've got 2 of those. So 2 there, so I'm going to times that by 2. In my products, I've got here C00, and that's in carbon dioxide. There's only one carbon dioxide, but carbon dioxide has two C00 bonds in it, which is why I'm timesing it by 2. And water has 2 OH bonds in it, but I've got 2 waters, so that's 4. And so what we do is we look at our CHs, and I see I've got 413, so I'm going to times that by 4, and I've got 2 double O's, and that's 498 times 2. So 1652, 996. I hope that's right, doing that quickly in my head. So 2648 for the amount of energy to break all those bonds. Then over here, C00 is 805. I'm going to times that by 2. Because of that there, 1610. And then OH is 464. You won't ever have to memorize any of these values. They'll all be given to you. Times 4. I'm going to give in and switch to a calculator. 3,466. So what I do here is I, again, go back to the previous. Average bond enthalpy equals energy required to break down the bonds, so 2,648, minus the energy given off. So 2648 minus 3466 equals minus 818 kilojoules per mole to minus 1. Another way is to have a look at it and go, well, this is a combustion, so assume it's probably going to be exothermic. So take either from the other, but remember then it's going to be negative at the end. And that's average bond enthalpies.